Okay, super. So thank you very much for the introduction. Very happy to be here. Very happy to hear all these interesting talks about philosophy, art history, physics, machine learning. And we've talked a lot about creativity. And here are two other words that are very hard to define as well. One we talked about this morning with Larissa, which is beauty. And the other one that we haven't talked so much about, which is complexity. And we try to see what we can make out of those two. Okay, it's not working.
Maybe click on the slide.
Okay, super. Thank you. So here are two images of mountain, lakes, and forest. And these two images basically are obtained by typing on Google beautiful images. This is the first two images that appear. For the anecdote, I've tried beauty before, but then you get a lot of cosmetics, which is really not the topic of my talk. So I refined my search and went to beautiful images. And I think if I ask the audience today, do you think these images are beautiful? I imagine the mass majority of you would say yes. And so the question that arises when you pose that sort of question is that, is there such a thing as universal beauty? Of course, we're not the first one to pose that question. It's been maybe posed for thousands of years. And coming back to Kant that we also had this morning, we talked a bit in the question about the concept of natural beauty. And so one of the things that Kant says is that the beautiful is that which pleases universally without a concept. So we see that beautiful and universality somehow are put together within the same sentence here. And of course, there is no consensus on that question. There is lots of debates among art historians, among philosophers, even mathematicians. But from the physics perspective, this problem has never really been tackled, and this is what we're trying to do today. Okay, so before jumping into the subject, let's talk a bit about what happens in some very important part of the art history, which is Renaissance. And Renaissance has at its core the very interest of beauty. And what's interesting is that the Renaissance principle partially rely on the mathematization of the artistic representation with concepts such as symmetry, proportions, geometric proportions such as the golden number. And if we just focus on symmetry for a second, we see that on this right painting, it's quite clear that there is some high level of symmetry in the image. And the same thing happened in the second one, because you see that the perspective gives you a very left-right kind of image. Maybe the number of persons are more or less the same on the right and on the left. And some of the patterns are repeated on the left and on the right as well. But what's important in what I just said is the more or less. It's not perfectly symmetrical. It's almost symmetrical, but there is some kind of, not chaos, but a bit of disorder in that symmetry. And it's even clearer in that image from earlier Renaissance. So you see from these panels, this is the original image. And if you zoom in, you see that what appears to be very symmetrical at the beginning actually has some level of asymmetry. You see that some of the characters are looking the other way. They don't have exactly the same beards. So what is interesting in that is that beauty at some level has a bit of disorder in that symmetry. Okay, and here are some quotes that I like about, two quotes that I will talk about now. One from Rudolf Arnheim, who is a German writer, a film theorist. He says, on the one extreme, the stiffness of complete standstill. So if I relate to the image that I have below, I would talk about the fully ordered white, very dull image that you have here. And on the other, the equally terrifying formlessness of chaos. So pure noise, fully disordered system. And somewhere at the ladder between the two extremes, every style, every individual, every artwork finds its own particular place. So here it's a bit specific on this quote because it talks about artworks. This is not really the topic of our talk, but if I have to put it in a more simple sentence made by a colleague of ours, Jean-Philippe Bouchot, total chaos is disquieting, too much regularity is boring, and aesthetics is perhaps the territory in between. There is nothing new about these concepts because this is something that has been discussed many times in the past. But what we are interested in here is, what does this territory in between mean? Like this intermediate, can we actually rationalize this? And this is what physicists try to do, rationalize the world, and we're trying to put some quantitative approach into that concept. Okay, so what do we do to do that? So first of all, we generate images. We generate two sets of abstract images. We will focus on the first one because we don't have much time to talk about the two, but this is the same thing. Like you start with a quite ordered system and you go into disorder, you increase the entropy of your images. For those of you who don't know what entropy is, a simple definition would be the amount of disorder in your system. If you take a matter and it's a gas state, the gas state is much more disordered, the entropy is higher than the liquid. So in this image, the disorder is much higher in the last image than in the first one. And so what we wanted to do as well is to remove the semantic as much as possible from the images. So we tried to generate abstract images. We'll see that it's not that easy to generate purely abstract images because we are as humans trying to simply grasp some content within the image, but at least we tried. And you go so from increasing entropy to from low entropy to high entropy. The other thing that we remove, as you can see, is the colors. It's purely black and white. Why we do that? Because we saw with Hortensia's talk yesterday that colors on its own, the color harmony is another subject. And we try to lower the dimensionality as much as possible. And so a bit like a Matteo's study, a survey that we will hear the result after our talks, what we did is that we did a survey about human preferences. So we asked people, can you select between two images, the one that you prefer? We did this on all images. So you have 6 images, so a total of 15 battles. And what we did is that we gave a grade per image simply on the number of victories it obtained. Very simple. Just a quick word about the survey itself. There are different ways to rank images. You could think about the usual 5-star system that we're used to when you judge a restaurant or a hotel or something. The problem here, if you do that, is that you don't have a reference. If I give someone that one of these pictures, would you put it a 5-star or 4-star at the beginning? It's very unclear. So we'd rather have battles. The other possibility that you could do is put the 6 images together and have people rank them by preference. The problem with that we imagine, that we guessed, is that people might sort the image not by preference, but especially by order, because there is some continuity in the image. So we prefer this a bit like more costly in terms of time, but at least avoiding those biases. And what we did, what we obtained are the following. So we plot the scores against that entropy, against these images. And what we see, very interestingly, is that there is no flat signal. There appears to be preferences. The sample from which we did these experiments were from colleagues, students in a very Parisian area. And I think the question was raised yesterday about cultural biases. So we obtain results, very interesting results, that these 2 intermediate pictures seems to be liked by most people. But okay, maybe there is a cultural bias there. Maybe it's the full signal. It's academia, it's a Parisian environment. So what we did is that we run the same test on something called Mechanical Turk. I don't know if you've heard about it. But for those who haven't, it's basically something where you ask people to make simple tasks. And so we ask people to just basically, we run that survey over Mechanical Turk, and when they finish the survey, they get paid a certain amount of money that you define at the beginning. And so we did that with people from all around the world without necessarily an academia background, and we obtained very similar results. And then we said, okay, but how can we ensure that these people didn't answer randomly? Because they get paid just for the task. They don't get paid for the quality of their answer. So they may have put left, just to get paid rapidly. And so what we did is that we asked another question, a bit tricky. We said, okay, imagine now that you have to choose the image that is the closest to what the average answer would be. So we asked somehow the question, what do you think that the images that would be preferred are closer to universality, to universal beauty? And we also said that if you're far away from the average, then you don't get paid. It's a bit tricky. Needless to say that we paid everyone and we paid them generously, but it was most to avoid that bias of people answering randomly. Maybe it introduces another bias which is not your own preference, but at least the concept of universality appears in that question. And again, we obtain very, very similar results. So what's interesting in there is that with a very simple set of images that are at least a little bit abstract, we obtain a signal, which was not so obvious at the very beginning. This is an intuition that we've had from thousands of years. But here is a proof with more than 1,000 participants that intermediate order, because I remind you that these images are ranked from low order to very high, to low disorder to very high disorder, that there is a signal of preference among people, and it's not a low signal, it's quite a strong signal. And interestingly, a little bit also like what the color talk yesterday told us about is that if you take these two images and you measure their level of entropy, their level of order, or in that case, what we call the roughness of the Hurst exponent, which is equal to 0, these images have a roughness exponent that is comparable to most of the natural landscapes, an image of a natural landscape that you have about. So it's not a proof that one is because of the other, but it's more like there is a strong correlation between what we like in those abstract images with what nature has to offer. And coming back to the semantic that I've talked about at the very beginning, when we asked people why did they choose those images, so some people said because it looked like it's balanced, it's well balanced. Okay, this is the goal of what we were looking for. But others were like, but because it looks like the Milky Way, it looks like a dense fog, it looks like clouds. So people are always trying to get back to what they're used to. So it's kind of hard to separate the two. Anyhow, there is signal. And then the problem is that when we look at that, we say, okay, disorder, if we look at these curves, disorder is not a measure of aesthetic preferences. Because it is at the very beginning somehow, but at the very end, it is not. We would like to have a fully increasing curve that would say, okay, fully disorder means fully preferenced. But it's not the case. So how can we get rid somehow of this last part of the signal, of that noise that we seem to dislike? And now I want to talk to actually introduce what we can build out of this. I would like to introduce this called the coffee automaton problem. So you take milk and coffee at the very right, you let them mix together, and then you have a latte, basically. But what happened is that if you look at the system from the microscopic point of view, the entropy is increasing. But if you look at the system from a picture point of view, the entropy is not increasing. At the very end, it's no longer that noise that we had and that we have at the microscopic level. It's more like dull and completely boring, resembling to what we have on the left. So somehow that coffee is telling us that there is a way, if we zoom out from our pictures, that maybe we can remove that noise that annoys us. And so we started with that idea, and we say, okay, can we define such a measure that will not be linked directly to the entropy, but more of the structure, of the richness of the images? And before going into that details of how we build such a measure, there is a term that we need to explain a little bit more, which is complexity. So complexity, the common use out of the context of science, is something that is either negative or positive. Two examples. If you say the situation is complex, it's opaque, it's complicated, it's rather a negative sense. But then if you say this painting is complex, it's rich, it's interesting, then what you have is a more positive aspect, a more positive note on what complexity can be. And then looking really at the definitions, so I think this one is from the Oxford Dictionary. Complex is which contains several parts or several combined elements in a non-trivial way, unclear at first impression. So a rather negative impression of what complexity means here. But then if you go back to the etymology of the word, so going directly to the verb complexity, it means to understand, embrace intellectually and physically. So rather a positive note. So you see that even in the definition of complexity, there are these two aspects that pop out. And in the science use of complexity, so there is a whole field of research which is called complex systems that I guess are very widely studied here. And complex systems, in scientific sense, are composed of a large number of constitutive elements, interactive without central coordination, without plans from an invisible architect, and leading to the spontaneous emergence of non-trivial structures. And these complex systems can be, for example, interacting spin models or fluid flows or socioeconomic systems. And then if you talk about complexity measures within the science world, you have both definitions. You can have disorder measures, such as entropy, compression rates, or richness measures. So the robustness to compression, the diversity of structure or configurations. And so now we need to define and to separate both definitions to make sure of what we're talking about. So the first thing is the entropy complexity. So somehow it's related to the order at which we generated the image. So the entropy complexity of the image that we generated is increasing. But the structural complexity is not, because the richness of the image is not that high for that very last noisy image. And this we need to define. And so coming back to the coffee problem, we have our three of the 6 images that we have here, and we're trying to somehow mimic what the coffee automaton does. And how do we do that? We first, okay, this is for the procedure, but we first threshold. So it means that we transform our images into purely black and white, because before there were gray levels. And then what we do is that what you might do when you squeeze your eyes a little bit, and you see that that very noisy image becomes only a grayish kind of dull image. And this is called coarse graining. A coarse graining procedure is something very classical in physics as well. And basically tells you that you take a point within your image, you look around it, you take a radius of, I don't know, a couple pixels, 5 pixels, 10 pixels, and you average out. So if it's mainly white, you keep it white. If it's mainly black, you keep it black. And if it's somewhere in between, at a percentage that you define, then it becomes gray. And when you do that, when you coarse grain these images, what you obtain are the 3 images that are here that somehow resemble our coffee automaton. And so somehow we can now define what the structural complexity is. It is the entropy of the coarse grain system, or at least it's one definition that we can give, because there are many definitions that you could give. But we're no longer looking at these images, we're looking at the final results here, where the interestingness, the richness, is only present in the middle and not here. And so this is something that we can compute. We can measure actually the entropy of these 3 images and the 6 images, because we did this process for the 6 images. And what we have is that of course you have fitting parameter to your thing, but you have something where you can get rid of the noise. These are the diamonds that you see here that somehow can follow much better the human preferences as a regular entropy would do. So there is nothing magical about this. It's just that we remove the noise from the entropy. So it's somehow noiseless entropy is a better measure of aesthetic preference that entropy is. Okay, so the conclusion.
What is it?
So the radius is a fitting parameter. The way you also define the percentage of how you transform it to gray or black and white. And I think that's it. Yeah. But
curve is not.
No, in the curve there is some fitting. That's why I will talk about that right now. In the diamond there is fitting. In the curve it's just raw results from the data.
And the fitting is on these sort of noising radii and kind of things.
Yes, exactly. Yeah.
Okay.
Yeah. And so we see that we match. We have at least we have a tendency that matches human preferences with that. So what does it say? It says that, okay, we are not answering the question of universal beauty, of course, but we saw first that there is a signal of human preferences among these 6 images, regardless of cultural biases or anything, and that we can build some kind of measure of metric that matches those preferences. But the thing is that with that structural complexity, the problem is that it's very dependent on that procedure, on that cross-graining procedure, and we would like something that is agnostic completely of any procedure. And so now we're going into a bit more detail into what kind of complexity we can build. And this is very related to, and with Matteo Marsili's work on this subject, and we have actually worked on that very specific subject together. And to understand what can be this, what we call multi-scale complexity, here is a simple example. So imagine that what you have is a variable that is between 0 and 1, or between -4 and 4 in that case, and you sample 100 points among this variable. So you have a data set of 100 points, and you ask yourself, how can I represent this data in the better way if I want to plot a histogram of this data? It's a question I think that we all asked ourselves when we began coding, like what is the better representation of my data? And the answer is not obvious. So what you do is like usually you just test an error. And so you do, okay, I will take lots of bins and I will put a histogram with lots of bins. But you see that here, the bins are containing only 1 or 2 points. So it's quite flat. It's not very interesting. On the contrary, if you say, okay, I want very somehow oversampled thing, I will take only maybe 3 of these bins, and then you have the graph that is there. But if you take an intermediate between those two, you have something that is somehow more representative of the data set that you were trying to represent. And we'll see in a second why we call it more relevant. So I don't want to jump too much into the details because it's quite complicated and it needs a talk on its own to be explained. But if we somehow look at something that we call the relevance against the resolution of this thing, going from that image, the A3, to the A1 going through A2, we see that this one that we said is somehow looks like the more relevant way to represent our data is maximized here. The relevance is maximized. And what could be even more interesting is to look at the area under the curve, meaning like we take the relevance at every single step of resolution, every single step of compression. And when we do that, we are really looking at the multi-scale relevance of our sample. So this was just an introduction to talk about this kind of concept. But now if we go back to our images are nothing less than a data set of, here in that case, of pixels associated with a color, a gray level. And so we can take any compression procedure and look at what we obtain in that MSR, multi-scale relevance case. So here the compression procedure that we took is basically, again, thresholding. So we threshold with black and white. In that case, A equals 0.5, but you can take any value and we'll see how it matters later. And then you can compress also by cutting the pixels into bigger boxes. And when you do that procedure on the textures that I've showed before, so they're actually reversed, but here is the more noisy, the more disordered one, and we go towards more order here. We see that these are the typical images that people tend to prefer, these random textures. And when you threshold and then you look at that curve of resolution against reference, relevance against resolution, sorry, the blue curve, which represents that one that we preferred, is actually the one that obtains the best result if you look at the area under that curve. So somehow, this is another way to define some kind of structural complexity of our system. And now going to natural images. So this is an image that is taken from another paper, and it was taken, it's like they were talking about evolution. And this is supposed to represent, in a better way, how humans have evolved. Like, because we were born, all of us in Africa, in a savanna environment. So this is a picture from the Okavango Delta. And we look at the different patches that compose this image. And if we look at the patches that compose this image and we apply a very naive technique in visual analysis, which is called power spectrum decay, we see that all these patches, although they look to us different, they fall into more or less the same curve. We don't have much signal that differentiates. But then if you take the MSR that I just told you about before of these images and we look within our compression procedure at the evolution of this curve, we see that we have much more signal appearing, something that we can actually analyze. What it means is that this technique seems to be a better way somehow, or a different way, to analyze the structure of these images. And what I want to finish with is this very beautiful idea that I think is very relevant in that context, which is if we take one of those patches, say this one, and we look at the evolution of MSR with that thresholding procedure. So if you are at low A, it means that you have a lot of white pixels when you're thresholding. If you have at high A, then you have lots of black pixels. And somehow, if you take the two maxima, so this one, the blue one, and the red one, and you display them, which are these images, which is not representative of that image, and that one, which is not representative of that image, and you put them together, you overlap them, then what you obtain is something that is very similar to the original image with only two very simple thresholded black and white images. So somehow it's the way to find the most relevant representation of that original image in a simplified way. Okay, so with that, I would like to thank you, and I'm happy to take any questions.
Thanks a lot for the talk. Questions?
Yeah, thank you so much. I just wanted to start with a little remark because it's super fascinating, because a lot what you were uncovering in that research matches with a lot of history and philosophical aesthetics, where there is this conception of uniformity amidst variety, which is maybe exactly what you are describing right now in physical terms. So I think it's like super fascinating how there's a match. And
Yeah.
I mean, we were talking about that yesterday. And I just wanted to ask, out of curiosity, so whenever I give a Kant talk on beauty, I try to defend that I'm using the concept beauty. So because it feels like, and Kant has such a concept actually,
Yeah.
because it seems to cover just a few instances that we label beautiful nowadays, and a lot of things drop out. And so I was just curious why you work with a label of beauty instead of, I don't know, aesthetically interesting or stimulating or something. Yeah.
I think the subtitle of my talk was like aesthetic preferences. So I agree that we are a bit we're missing a bit too much the two concepts of aesthetics and beauty. You're right. So maybe we should have taken the word aesthetics from the very beginning. And actually, in the way we presented, maybe in the way we present, we use a lot the word beauty, but in the way we ask the question is only which one do you prefer? Yeah, we never say which one do you find the most beautiful. And so it's really a matter of human preferences. And when we are a bit accurate about what we're saying, we are putting scores against human preferences, not beauty.
Okay, other questions?
This was beautiful. Thank you very much. So I just have a question about the figure you showed. I think it was slide 20 or just at the beginning of your presentation, which is the evolution of the score with the degree of disorder, if I understand correctly.
Yeah.
And then you have three populations, to Amazon Turks and academics. Yeah, exactly that one.
Yeah.
So I was wondering if you see any dependence on the cultural background, geographic location, or if you have looked into that.
That was exactly our question at the beginning. When we did our first test, it was okay. These are people from maybe the same background, so maybe there is a bias there. There was people from mostly France. I mean, not only French people, because in labs you have people from all around the world. But then we ran the test in Mechanical Turk and etc. We didn't look at if your remark is like, did we subset the data to see if people that were coming from India had different tastes that were coming from the America? We didn't do that, but I think we didn't do that because this is most of the PhD work, and I don't remember if he did that. But I'm quite sure that there is no signal. Like in that abstract images that we show, people from India would answer the same as people from Japan.
Yeah. Thank you.
Yeah.
I also have a curiosity about the final measure you introduced. It looks to be very powerful, and can it be used for data analysis to just find interesting structures in the data?
Definitely, and I think I will let Matteo answer to the question because he's more of a specialist. But yes, definitely, it's made for like we supplied here to our image problem. But I think the first thing that you start working that was in neural networks, I guess, and then it was applied to biological systems, to wherever there is data and there is possible relevance to that data that can be extracted, then you can apply this method. Yeah. And we just used it in our case to build a more refined structural complexity that would match human preferences.
Thanks. Okay, let's thank the speaker again.